So let's start. Yesterday हमने just इससे degree of hardness मैंने आपसे कहा था कि numericals you might have done before. Hydrogen peroxide. Hydrogen peroxide का structure is extremely important for exam. It has been asked. This is what I have drawn and this is what given in NCERT. So I have taken both here for you to refer. 2-3 years back, you know that this exact dihedral angle and bond angle were asked. So this given in NCERT clearly in gas phase, okay, it is a book-shaped structure and the angle between the two planes as shown in the picture is known as the dihedral angle. Correct? In gas phase, this dihedral angle is 111.5, whereas in solid state, it comes to 90.2. You can see just opposite. In gas phase, dihedral angle is greater than OOH bond angle, which is 94.8. Whereas in solid state, this bond angle is greater than dihedral angle. Okay? So just observe this comparative diagram which is shown in NCERT. It will be asked, it can be asked rather instead of it will be. Okay, so dihedral angle in gas phase is 111.5, whereas in solid state it is solid phase it is 90.2. Okay, I have made this comparative thing also that OO bond length kahan zyada hai, OH bond length kis phase mein zyada hai, and bond angle. This particular page will be very important for you as a short note when you are at the last moment revision. Okay, so please go through it. Moving to next. Yes, you should remember that both the hydrogens are present in different planes. I hope that is clear by now. Coming to the preparation. Preparation of H2O2 again is asked off and on. So barium peroxide is taken and is made to react with acid like H2SO4. You cannot take acid like HCl, otherwise the chlorine in it can be oxidized to Cl2. So we have to take such acids like which cannot be oxidized further. Is tarah ka acid we use, and simple we get barium sulfate, which will be a precipitate, can be removed water, H2O2 and water. Okay, so H2O2 preparation is done by this barium peroxide salt. Okay, H2O2 you can remove, but remember the H2O2 removal is to be done under a very reduced pressure condition. To increase the concentration of H2O, removal should be done in a very reduced pressure condition. Otherwise, when you will do the evaporation, do the heating, H2O2 may decompose. So increase in the concentration of H2O2 here can be achieved if you do the evaporation of water under reduced pressure. Okay? Yes, you can have other methods like hydrolysis of peroxides and superoxides. Even superoxides, if hydrolyzed, will always generate peroxides liberating oxygen gas. तो अगर आपने peroxides लिए तो भी आपको H2O2 मिलेगा, superoxide लिए तो भी आपको H2O2 मिल जाएगा. This another method is used frequently by hydrolysis of peroxodisulfate, K2H2O8 जैसे salts जो हमारे हैं, we can do their hydrolysis and then electrolysis. ठीक, peroxodisulfuric acid is obtained by electrolysis of H2SO4. ठीक, like this. First we make this and then after doing this, we hydrolyze it. Okay. But if you want to make D2O2, then instead of normal water, you will use heavy water, that is D2O. If you want to make simply H2O2, then here you use H2O. Whichever is your aim, as per that, you can decide here you want to use H2O or H2O2, right? Industrially, H2O2 is prepared by 2-ethyl anthraquinol method. Now what we do, this is a very low cost method. We take this 2-ethyl anthraquinol. Okay, position number 2 pe we have added ethyl. So it is 2-ethyl. You can have some other alkyl, no problem. So by air oxidation, it is changed to anthraquinone. There has to be one more line here, right? These two independent aromatic structures are formed. This oxidation is quite easy, and this oxidation takes place in presence of air itself. And when this oxidation takes place, just let me use another color. So like this H and H. You know oxygen acts as a biradical, right? So here, like this. Okay. And this oxygen takes these hydrogens. So you get H2O2. And this is how this anthraquinone is formed. Now it is a very useful method because by sheer reduction using metal hydrogen combination, you can regenerate the anthraquinol again and then again air oxidation. And so it can be recycled, and overall it becomes efficient, cost efficient. So it is industrial method for preparation of H2O2. H2O2 is commercially important compound. So we need industrial method. In this, though, we get only 1% H2O2. The concentration is quite less. That is nearly 30% concentrated H2O2 is obtained by this. है ना? उसका 1% H2O2 हमें मिला और हमें 30% जब चाहिए, मतलब we need to increase the concentration of H2O2 in the resultant. Then what we have to do? We have to distill at reduced pressure. ठीक, अगर हम ऐसा करते हैं तो we can get up to 85% by mass concentrated H2O2 आपको मिल सकता है. That is very nice. But it entirely depends, do we want to go for this increase in concentration based on where we want to use. Okay, if we want to use as some medicinal importance or something where it high concentration is required, then only we do this. Otherwise, we don't want to add the cost. Physical properties of H2O2, it is when pure is colorless and of course liquid at room temperature, miscible in water, form hydrates like this. H2O2 decomposes slowly on exposure to air. Okay, as it is a peroxide. All peroxides on exposure to air decompose, releasing oxygen gas. So that is why H2O2 is stored in bottles which have either the wax coating, we add some urea in it so as to inhibit or so as to slow down its decomposition. Okay, wax lined glass or plastic vessels, we also want to put them in dark because light catalyzes their decomposition. Okay, urea, as I said, we add some urea into that bottle because it stabilizes H2O2 and its overall decomposition is slowed down. Volume strength, I assume you might have done in mole concept. If you have not done, I have shared notes. This part is there in your notes, which I have shared in the note. Coming to next, this point. Let's see the physical properties of hydrogen peroxide. If you see its melting point, its boiling point, right? Vapor pressure, density, I think everything is almost everything is greater than water. Okay, correct? So that you can see and compare. What is being asked from H2O2 is usually this chemical properties of H2O2. H2O2 can act both as oxidizing as well as reducing agent. Okay, that is an important property which is questioned. Some of its example. For example, if I talk in acidic medium, then see Fe2 plus is oxidized to 3 plus. So it is here acting as a oxidizing agent. Whereas if you see here, Manganese plus 7 of KMnO4 is reduced to Mn2 plus. So manganese is reduced. So in this reaction, H2O2 is acting as reducing agent. It can act as both, as the oxidation state of oxygen is in between the two extremes possible for oxygen of -2 and positive. Okay. Going further, basic medium may be, you can see, basic medium may also you can see this type of redox. Fe2 plus, say this iron is oxidized. So H2O2 is acting as oxidizing agent. For iodine, you can see it is being reduced. So here it is acting as reducing reagent. Okay. Again, qualitative analysis, an important reaction there. PBS, if made to react with H2O2. Okay, remember you will not get sulfur turbidity, you will get PbSO4. Here the sulfur of PBS is oxidized directly to +6 of sulfate. So here H2O2 is acting as oxidizing agent. Okay, if you take HOCl, hypochlorite, and H2O2 is made to react with it. Here chlorine is in +1. Now in result it is Cl minus. So it is acting here as a reducing reagent. So overall H2O2 can act both as oxidizing and reducing reagent. Okay, these are the observations of what we have seen till here, that how it changes in different medium. It means H2O2 changes itself. Clear? Moving to next, that is use of H2O2. H2O2 commercially is sold by the name perhydrol, and this is the common most name that you can buy H2O2 over the counter using this name. Medicinal shop पे भी आपको मिल सकते हैं. Disinfectant है and a bleaching agent for textile, paper pulp, etc. Yes. Manufacture of sodium perborate, percarbonate, pharmaceutical, hydroquinone, and tartaric acid. It is used in these industries. It is used for treatment of domestic and industrial effluents, oxidation of cyanide, restoration of aerobic conditions of sewage waste. Okay, we use it for the, what should I say, to improve the condition of places where we have placed sewage waste, so that when you add H2O2 there, increase in the oxygen concentration, and thus the aerobic condition of that particular place can be improved using this. Okay. Last point of hydrogen was D2O, heavy water. By exhaustive, this line you have to remember, D2O is prepared by exhaustive electrolysis of water. Okay, exhaustive electrolysis of water, say you have D2O. As a byproduct in some fertilizers also it is produced. It is used as a moderator in nuclear reactors, right, to decrease the speed of the neutrons, to study reaction mechanism in exchange reactions. Yes, isotopic use karke we want to track mechanism, there we can use it. For preparation of other deuterium compounds. For example, I want to prepare acetylene. Now my normal acetylene, when I say, I will say CH triple bond CH. But I want to have CD triple bond CD. Then I will take calcium acetylide and add D2O. So I can introduce deuterium here. Similarly, I want to have methane. Instead of this H, I want deuterium. So I have L4C3 and CD4 is placed. See? Now see, as I told you, questions have appeared on the preparation of all decomposition of hydro. If you see, you have to identify the correct ones. You will see anthraquinone thing is asked. Okay. How it reacts is asked. Its decomposition is asked. So this is how the questions of H2O2 can be framed in multi-correct options with each property. Okay, you will get all these questions in your notes, physical properties of D2 and H2O. Again, I will say, as we have talked in isotopes, right? Similar way, you can again see heavier isotope has higher properties. And I do not find even single exception in this entire table, except for the dielectric constant. We have already discussed this yesterday also. And again in D2, I am reiterating that except for the dielectric constant, for all other properties, higher mass, higher the numerical value of that property. Okay. So that brings us to the closure of hydrogen. Let's now start S block. Okay. Now S block, we are given 2 days, good enough. I will say hydrogen number of classes and S block number of classes are almost equal. So at least here we have 2 days. We'll try to complete alkali part, first group part today as much as possible, and today it will be, tomorrow it will be easily completed. Okay. Plus hydrogen has such things which are applicable in different groups. S block, you know already a lot of things. Let us start. You already know that S block has 2 groups. Why it is called S block and all, I'm not entering. I have written them. If you want, you can read, but I'm not discussing. So S block has 2 groups. First A, in old nomenclature I'm saying, and second A. In the new way, it is first group and second group. The first group is named as alkali metal. The second group is known as alkaline metal. But yes, when we use the alkaline earth metal nomenclature, then beryllium is excluded from this nomenclature, because this name alkali and alkaline is referred to their hydroxides or most of the compounds which are highly alkaline in nature. From that, they have given this name alkali metal and alkaline earth metals. But as beryllium will be more of amphoteric in nature, so it is excluded from this name alkaline earth metal. If you use simply second group, then beryllium is very much part of this term second group. ठीक, groups में members क्या है, you know. Let us come to the important points that could be asked as a factual information. So francium is radioactive and its half-life is further very small, only 21 minutes. ठीक? So in general, I cannot have a lot of concentration of francium present today on Earth to have a lot of the general studies. So general studies, whenever I comment on the general studies, please exclude francium from it by default. And similarly exclude lithium from first group analysis, and second group में जब बात करें तो beryllium by default. For everything, I will have to say in first group except lithium. In second group, I have to say except beryllium because of their diagonal relationship with the diagonally placed. For lithium, I'll say magnesium. For beryllium, I'll say aluminium. So they will not behave like their other group members. Electronic configuration, yes, NS1, we all know. Coming to atomic size simply increases down the group. See, in their respective group, increasing down the group. Along the periods, they will have the largest size or the largest atomic radii in their respective period. Of course, the size of their cations will be definitely smaller than the parent atom because a complete outermost shell is removed. If we talk of their electropositive nature and ionization energy, certainly, as I have already told, they form basic hydroxide. They are all metals. So they are electropositive metals in nature. Electropositive, they have low ionization energy also. In their respective periods, they will have the least ionization energy. And if I talk in the group, down the group, if I talk, I'll say down the group, their ionization energies will further decrease due to increase in size of the atoms. Okay, that is general. And due to this property that down the group their size increases, ionization energy decreases, cesium and potassium are used in photoelectric cells, right? The outermost electron can be easily excited. their second ionization energy will be extremely high because by the loss of one electron, they attain noble gas configuration. And thus, their second ionization energy will be very, very high. I will go to the table of their physical and other properties. There, I want you to have a little information. I'll add that. Okay. Abundance, if we see in nature, sodium out of these is most abundant, then potassium. And sodium and potassium, these two are extremely important for our biological functioning or biological functioning of the living systems. Whereas these, rubidium, lithium, cesium, and francium, inka availability goes on decreasing. Okay, francium is very, very less available. Yeah, here it comes. So I was saying atomic and physical properties. Now, what I wanted you to know, see their ionization energy. And here they are talking only of first ionization energy, 520, 496, continuously decreasing, 419, 403, 376, minus 375, continuously decreasing ionization energy they are talking. Well and good. They are not talking of the second ionization energy, which probably will be 3 to 4 times or maybe even more, because then you have to remove electron from the from the noble gas configuration. Okay, so just remember that if there is a vast gap of ionization energy 1 and 2, take that hint that the unknown atom or the metal or whatever is mentioned in the question must be from alkali metal group. Okay, now coming to density. Where is the density? Here is the density. Its density do not show that regular feature here. See here. Okay, if you see density, down the group, I can say density somewhat, I can say increasing. Okay, though not regular. See, cesium is highest, 1.9. Then it is rubidium. Fine. Okay, then it is sodium. Okay, it is not potassium. Potassium is less than sodium. Potassium ka density is less than sodium, and then it is lithium. Okay, now why this observation of potassium density less than sodium? Because increase in size from sodium to potassium is dominated over the increase in mass. What is density? Density is mass upon volume. When you move from sodium, which is third period, to potassium, which is fourth period, the sudden increase in size dominates over the increase in mass. So in particular, this place, you observe a little hiccup in the order. Rest, it is okay. Lithium, sodium, and potassium, all lighter than water. See, lithium, sodium, potassium, all lighter than water. But rubidium and cesium are denser than water. Density increases down the group, we have already discussed. Okay, so moving to melting boiling points. Melting and boiling points, I can make a clear statement. There is a continuous decrease as we go down the group, right? So there is a lithium, sodium, potassium, rubidium, cesium continuous decrease. Yes, overall decrease in the group, lithium is relatively having a higher melting point, well and good, but overall they are all very soft, very low MPBP, and they can be cut by the knife. See, as they are reactive towards air, and that is why are stored under kerosene or any other hydrocarbon which is unreactive to them can be used. Now, this is important. Standard oxidation potential from M to M plus I'm talking. This is important. Please observe this. Okay. If I see this, here they are saying reduction potentials. I'm stating oxidation. So I'll just revert their signs. Okay. So if you see from here, you see Li plus to Li minus 3.04. So Li to Li plus, it is plus 3.04. So the ease of oxidation from lithium to lithium plus, despite having highest ionization enthalpy, is highest. I hope I have made my Oxidation potential from lithium to lithium plus is highest, though it has the highest ionization energy. And then the credit goes to its high hydration energy. Because when you talk of electrode potentials, it is not just ionization energy which plays the role. You have the sublimation enthalpy, you have the hydration enthalpy along with ionization. Okay? So lithium becomes the strongest reducing reagent with highest standard oxidation potential of plus 3.05. Remember that. Sodium is the weakest. Sodium in the group is the weakest. See, sodium, where is sodium? Minus 2.7. See, all other are 2.9. Okay, so sodium is the weakest in the group, take as a reducing agent with lowest standard oxidation potential of plus 2.71. Reason why this happened? Because of the combination of these. Lithium becomes the winner because of high hydration enthalpy. Okay, it becomes the winner due to high hydration enthalpy. And similarly, potassium, rubidium, cesium becomes the winner due to low ionization energy and sublimation enthalpy. That is why they become the winner, and sodium becomes marginally though, but still, if order is asked, I'll say it is the weakest reducing reagent in the group. Okay? Here I have pointed out the reason again. Lithium plus is small ion with high charge density and thus has the highest hydration enthalpy, which accounts for its highest E standard value from M to M plus and thus making it strongest reducing reagent. Okay? Moving to next. Hydration energy, I think we have already discussed that with increase in charge density on a metal ion, its hydration energy will be high. Now, as we go down the group, size becomes large, charge remains unipositive, so charge density will decrease. So lithium will have the highest hydration energy. Now, lithium here is again, I would say, important, or you should take a note of it, that due to its diagonal behavior, due to its small size, it also forms hydrated salt like this, which, or rather, most of its salt remains hydrated like this, which is not the behavior with entire first group. You will not have this type of behavior with entire. And iska high hydration is why most of the lithium salts will be hydrated, like magnesium. Magnesium ke bhi maximum salts are hydrated. MgCl2.6.8 up to 6 to 12 हो सकता है उसका हाइड्रेशन, वैसे ही LiCl2 का UC.2H2O. Okay, flame color important, but I assume ये सबको याद ही होगा. It must be on your tips that this is because of the loosely held electron in the outermost shell. They will go to the excited state, and when the electron comes back to the ground state, it releases energy in the visible range. You have to remember the colors. You have to remember the colors. ठीक? Lithium, crimson red. Sodium, specifically golden yellow or yellow. Potassium is lilac or violet. Rubidium is mentioned to be reddish violet. Cesium is more towards blue. That is the brinjal wala blue is what we get in cesium. Okay. So just memorize the colors. They are important when the questions are asked about these things. Okay. Physical state, soft, silvery white conducting metals. Freshly cut will be lustrous but will be tarnished on exposure to air. Okay. Coming to reaction or the chemical properties of alkali. Now, as they are extremely reactive, as soon as they come in contact with air, out of the entire air components, the usual one, the nitrogen, hydrogen, and oxygen, it is the oxygen which reacts with them fastest, forming oxides. Based on the conditions, I will say peroxide and superoxide. Lithium is the only one which, along with oxide, can form nitride also, like second group members like magnesium. Excluding that, first I'll talk. So with oxygen, they burn vigorously in dry air. And when they burn in air, they form oxide, peroxide, and superoxide. Yes, the tendency towards superoxide formation goes or increases down the group. Smaller cations form oxide only. So lithium forms only oxide, Li2O, because small size, high polarizing power of the cation. When you go from oxide to peroxide and superoxide, size of the ion increases, right? So you need a larger cation to have higher lattice energy and thereby stabilizing that particular salt or a compound. So lithium cannot form peroxide, superoxide. Sodium forms monoxide and peroxide. Two it forms. Okay. I remember in NCERT it is given some superoxide is formed. Don't get into it. Okay. The two questions related to this particular thing which appeared and may confuse you. Let me take you what I was saying. ये कौन से क्वेश्चन का मैं बोल रही हूँ 2016 में एक आया था. Let us see 2020 में एक आया था. On combustion of lithium, sodium and potassium in excess of air, the major oxides. So don't get into the idea that by any chance should we consider sodium to form superoxide? No. Lithium only oxide, sodium oxide and peroxide, and potassium, rubidium and cesium you can consider their superoxide. Okay, so 2020 it came. It also came similar questions in 2016 also. Same language, excess of air. Again, the main oxide. They are not asking any oxide and not the minor ones and all. So the question, same concept has been asked. Please maintain that they are asking major existence of with oxygen compound. Okay, coming back to where we were, give me a second. So here we are. So potassium, rubidium, cesium can form oxide, peroxide, and superoxide. Superoxide ion will be stabilized only by larger cations. We have already discussed. As far as the oxides are concerned, formula is M2O, oxygen is 2 minus. All of them are basic oxides because alkali metals हैं. कैसे? How can we say they are basic? By addition of water, yeah, on their dissolution in water, what happens is they form hydroxides, which are basic in nature. Oxides of first group are exceptionally stable towards heat. They can also be obtained on heating peroxide and superoxide. If you heat peroxide, superoxide, you will get oxide with the liberation of oxygen. All the oxides are diamagnetic, including lithium and colorless compounds. There is no exception related to this. Okay? Coming to peroxides. Peroxides are of sodium, rubidium, cesium, and potassium. Okay? Peroxides are also colorless and diamagnetic because O2, 2 minus. O2 has 2 unpaired electron. When we add 2 more electron in this molecular anion, everything becomes paired, so it is diamagnetic. But yes, sometimes very old sample of peroxide may acquire pale yellow color. Okay, peroxides can act as oxidizing agents. We have already discussed because on heating or addition of water, they liberate oxygen, and this oxygen can be used for oxidation. Coming to superoxide. Superoxides are formed by potassium, rubidium, and cesium. Formula MO2. Important point to remember is superoxides are, let me underline, are paramagnetic. Okay, and colored. And their color is very standard, yellow, orange. Potassium, rubidium, potassium and cesium are yellow, orange. Rubidium is brown, but these two are specifically mentioned in NCERT. The potassium, cesium, the color is usually yellow and orange. Again, why they are colored? Because superoxide, one unpaired electron is present in pi star 2p orbital. So, uska excitation, de-excitation generates color. Okay? This is an important note. KO2, that is potassium superoxide, if further absorption of oxygen is facilitated somehow, an orangish red या ruby red color is formed, जिसे हम कहते हैं potassium ozonide, KO3. When it is hydrolyzed, it is a source of ozone forming QH. Okay, so potassium ozonide is formed by KO2. KO3 is also formed by a reaction of dry powdered KOH with ozone directly at low temperature, but very low temperature. Now, this is important. Oxidizing power definitely superoxide, सबसे ज़्यादा. Then it will be peroxide. Then it will be oxides. Oxides are not even oxidizing. And if you have ozonide, which is only in case of potassium, I would say, so then highest oxidizing power will be of ozonide. ठीक? KO2. What is KO2? Potassium superoxide. How will you check? You will immediately say potassium remains as +1. So you will immediately in your brain do it is -1. Okay. O2, 2. So 2 minus like this. Okay. This whole thing is -1. O3. So this is how you will see. If this is coming O2 pe -1, it is superoxide. O2 pe -2, it is peroxide. So superoxide is used in space capsules, submarines, where there is deficiency of fresh air supply, I would say, and breathing mask, because it has two things. It can function doubly. It both produces O2, right? When it reacts, it produces O2, okay? And it also absorbs CO2. See, KO2 absorbs CO2. It forms carbonate and O2 is released. So double thing, air को purify कर रहे, impure चीज absorb करके, and also releasing the good air, which is oxygen to the surrounding. Okay, so KO2, that is potassium superoxide, is used in submarines. Coming to reaction with hydrogen, alkali metals, they react with hydrogen, I would say, except lithium. I will, for others, I can say around 400 degrees centigrade, they will react, form ionic hydrides. Lithium can react, but around 1100 Kelvin. Temperature is much increased, but yes, can be react. LiH is useful, or we have already done yesterday that these saline hydrides are useful for preparation of other important compounds like LiLH4, NaBH4. So they are useful for preparation of other important compounds. And they are also source of hydrogen, done yesterday. Moving to next point, reaction with nitrogen. Now, no other alkali metal react with nitrogen. Only and only lithium reacts because of its diagonal relationship with magnesium. Lithium, sodium, potassium, rubidium, cesium, and francium, right? Magnesium, calcium, strontium, barium, and radium. So this diagonal relationship makes lithium to behave like second group magnesium. Here, all of them react with nitrogen of air forming nitride. So lithium also reacts with nitrogen forming Li3N formula nitride. It is ionic. And Li3N also ruby red color. Again, colored nitride is a very important information to identify whether they are talking of second group nitride or lithium nitride. Okay, so lithium nitride is specifically ruby red. It is ionic, well and good. If you heat, it releases nitrogen. Okay, but heating is not that simple. It is not warming. It needs strong heating. But the important thing, if you hydrolyze it, it can be source of ammonia, forming lithium hydroxide. Basic solution is left. Okay. Reaction with water. They all react violently. With water, hydrogen gas will be released. It is a redox. Metal is oxidized. Hydrogen is reduced. That is fine. As we go down the group, the reaction becomes more and more vigorous and explosive. Down the group, it becomes explosive and exothermic. As melting point decreases down the group, what happens? They come into contact with water more easily and thereby reaction rate increases. Okay? So they melt on the surface of the water and the reaction becomes faster and faster down the road. Now, as this hydrolysis is resulting into NaOH, so I'm discussing NaOH here itself. NaH is called caustic alkali and KOH is called caustic potash. This word caustic because it causes damage to your skin. That type of property of any compound is called being caustic. Okay. NH is a white crystalline solid. Chane ki dal. It has appearance of chane ka pulse appearance, size I want to say in lab. That is how it is placed in lab. It is stable towards heat. It is corrosive in nature. Highly basic, certainly. It is so strongly basic that it liberates ammonia not only from salt, but it displaces ammonia even from most of the coordination complexes also. See, NaOH say you are treating this cobalt complex. Ammonia is liberated free and CO2O3 is formed. So it is highly basic. Okay? All the hydroxides are basic. And down the group, their basic nature further increases due to increase in electropositive character of central metals. Okay? As they are base, they will react with acids. They will react with acidic oxides also. Okay, so they will react with acids and acidic oxides. This is different. This is important. Kindly remember this. Solubility of hydroxide in water increases down the group. Okay? Solubility of hydroxides. See, lithium hydroxide. Take sodium, potassium, rubidium, cesium. It is increasing. Lithium is only 5 moles per liter soluble. NH is soluble to 27 moles, 5 times more soluble. So down the group, their solubility increases. NaOH being a strong base, it can also react with amphoteric metal. I think all of you know that, and liberating hydrogen gas. It reacts with non-metal also. Okay? Like phosphorus, like chlorine, and important reactions when it reacts with phosphorus. This reaction has been asked, I think, hardly a year or two back in advance, right? PH3 was further made to react with copper, forming a CO, forming Cu3P2, and was asked how much amount of this Cu3P2 was formed, right? So NaOH P4 reaction, P4 is disproportionating NaH2PO2 and phosphine. This is a gas. If you make sulfur to react with NaH, then you have Na2S2O3 and Na2S. So non-metals are undergoing disproportionation usually in NaOH. Yes, it can react even with neutral oxide like carbon monoxide because it is highly basic. But then how it reacts? It forms sodium formate. Reaction goes somewhat like this. Okay. NaOH, as I said, is caustic or corrosive. So how it is having that property? It breaks the protein of the skin. When its solution, concentrated solution, comes in contact of the skin, then it breaks the protein, and protein break करने से paste like mass of that part is formed. It dissolves your body part, right? So that is why it is termed caustic properties. Caustic का meaning ही होता है able to burn or to destroy things by chemical reaction. Okay, it is very critical in a cruel way, in a bad way, it works on your body. NaOH is hygroscopic, that it absorbs water and forms hydrated compound. Okay? NH being basic also absorbs carbon dioxide when placed on the table. If you leave NaOH on table for days in continuation, from solid NaOH, after some time it will start getting a like semi-solid. You just let it be. It will keep on absorbing moisture from surrounding. You will have a clear solution. Don't touch. Let it be. Leave it on the table. After that solution, after a few days, you will find amorphous type white powder on the table. Okay. So it will absorb CO2 and will become Na2CO3. So it absorbs water and then it also absorbs CO2 from surrounding. NaOH is prepared commercially by the electrolysis of brine. Okay, by electrolysis of brine. Now, NaOH is commercially a very important compound. So there is entire industry to have formation of NaOH. Okay, पूरी इंडस्ट्री है, क्लोर अल्कली इंडस्ट्री है जो इसके यूज में आती है. So there is a complete industry and we have chlor-alkali industry जिसमें ये reactions होती हैं. Now, yes, NaOH you can prepare by this method, but NaOH and chlorine are still reactive and difficult to obtain them separately. So थोड़ा problem होता है इस industry में, but we somehow make it. Okay, that is a drawback of this general apparatus. You just do electrolysis of NaCl. At anode, you will have chlorine. At cathode, you will have hydrogen. That is a general reaction. This is an old method, but I will write here that this is outdated. We don't use it anymore. It was once used. Okay, called Nelson cell method, diaphragm method, currently of no use. This is what we use, Kastner-Kellner process, also called mercury cathode process. Okay. Now see here, these anodes, ये जो दिख रहे हैं ना hanging, these are of graphite or carbon. Okay. And see bottom, floating cathode. This is mercury. Okay. Chlorine is liberated at anode. It will come here. So it can be released from here. Okay. Sodium will go to cathode. Now here it is a mercury. So practically the sodium will dissolve in mercury. You will have the amalgam at cathode. Right? This method is much better because we are not producing NaOH here itself directly. हम यहाँ नहीं बना रहे, हम यहाँ सोडियम इसमें रखते जा रहे हैं. ठीक? Sodium amalgam is separated and is decomposed in a separate container. So we take out this cathode, we pump out, we release it, add into a separate container. Water add karte. When you add water to sodium amalgam, okay, sodium will dissolve NaOH, hydrogen will be released as a gas, and mercury being insoluble in these conditions will remain there. Now you can filter out the mercury and recycle back in the cell. So this is what we use. Now there is no such problem of impurities or NaOH coming up along with chlorine, right? So today what we use is we use Kastner-Kellner cell, which is also known as mercury cathode process. Please remember, cathode is of mercury, anode is of graphite or carbon. Brine remains same as electrolyte. Take. What about KOH? KOH resembles NaOH in all the reactions, but is expensive, so is preferred less in laboratory. Okay, just because it is expensive, so we avoid it. Moreover, it is also a much stronger base, so it will again have difficulty in handling and managing. It is prepared by electrolysis of aqueous KCl, the way we have prepared NaCl. It will be more soluble in water, in alcohol. NaOH is sparingly soluble, but KOH is highly soluble. Okay? I'm not saying it is ionizable or something. It is ionizing alcohol, and that is not what I'm saying. I'm simply saying it is soluble. As a reagent, KOH is less frequently used, but in absorption of CO2, KOH is preferably used compared to NaOH. Why? Because KHCO3 formed is soluble, whereas NaHCO3 is insoluble. And if NaHCO3 is insoluble, where we use all this CO2 absorbing things, space में, submarines में, space shuttles में, submarines में, या ऑक्सीजन सिलेंडर वाले जो डाइवर्स यूज करते हैं उनमें. So we don't want to have their pipes or tubes blocked by the insoluble NHCO3, by the deposition of NHCO3. Whereas KHCO3 being more soluble, it won't form such depositions and choke or block the tubes. That is why KOH is preferred over NaOH. Okay. Next is the reaction of alkali metals with liquid ammonia. Very, very important. All of them dissolve in ammonia, and when they dissolve, see here, when they dissolve, they form blue color solution. Okay, so when metal is dissolved in ammonia solid, what we get is we get electrons, which is dissolved in ammonia. We get M plus. This AM is ammoniated. Like aqueous we say, na? I'm writing ammoniated. So all of them dissolve, and what happens? This solvated or ammoniated electrons are there. Ammoniated cation is there. But this blue color is due to ammoniated electrons. As there are free electrons, so this solution will act as a very strong reducing reagent. All of you remember Birch reduction. This is what we use there, na? Ammoniated electrons. Okay? But yes, if you leave this solution, do not use for reduction, or you start heating it. And if you heat it or you leave it, then these ammoniated electrons react with ammonia. Hydrogen is released from here, and NaNH2 is formed. Okay, these start reducing H plus of ammonia itself if you do not use or consume for something else reduction. And if you leave this solution, well and good. But if you want to increase the concentration of metal, then this blue color conducting solution becomes bronze. Okay, increase in concentration of metal, then bronze ho jata solution. This whole thing has one exception, which is lithium, because it forms amide of Li2NH. All other forms amide of MNH2, but it forms Li2NH. Okay. Reaction with halogens. All of them react vigorously, fine. Lithium halides are somewhat covalent due to high polarizing power of lithium. Lithium iodide is the most covalent. Yes, well, but yeah. Properties. High melting, because ionic salts hote hain. Colorless crystalline solids. They can be prepared by direct halogen ka reaction on metal, by reaction of HX on oxide peroxide, HX on hydroxide, carbonates, bicarbonates. This page is important. This slide is important. I'm marking like this. All of these halides have high negative enthalpy of formation. Delta H formation value for fluoride becomes less negative as we go down the group. Okay, when we go down the group, then delta H formation of fluoride become less and less negative. Whereas upper and higher in the group, it is more and more negative. Reason, with the difference in the size of an anion cation, the stability decreases. See? Whereas the thing for other halides is just reverse. See? Because they are larger anion. If you talk of the same metal, then delta H formation becomes less negative from fluoride to iodides. Melting point, boiling point, fluoride, chloride, bromide, iodide, lattice energy factor, and ionic character. Okay. If you talk of solubility in water for group 1 halides, all these are water soluble. LiF shows relatively low solubility due to high lattice energy. Low solubility of cesium iodide is due to small hydration energy of large sized ions. Okay. In general, for LiF बोले तो lattice energy use करना. In general, for cesium compounds बोले to use the term hydration energy. छोटा cation lattice energy, बड़ा cation use the term hydration energy. ठीक. NaCl general properties, table salt है, बहुत बढ़िया. Nothing important, but yes. If you talk of NaCl, NaCl is not hygroscopic or deliquescent. Remember that. Okay, or deliquescent. Because of the impurities of CaCl2 and MgCl2, it appears or it gives us a misinformation that it is hygroscopic and deliquescent. That is the only important point I want to quote. Okay, NaCl solubility is quite high and it does not increase much on increasing the temperature. Dissolution of NaCl is endothermic. It absorbs heat. Okay. Now, these are the general formula. NaCl is not having dot H2O, but LiCl2 has 2.2 H2O. Okay, that will be there. Reaction with acid, they are all highly electropositive metals. So with any form of protic acid, they will release hydrogen forming respective salts. They can also form polyhalides, like Ki3 is very famous. Others are like this. Now, this particular halides of first group metals, when react with halogen or interhalogen, then they can form polyhalides. Okay. Oxosols of halogens, to some extent, I'll say yes, important, particularly carbonate bicarbonate, except for lithium carbonate. All are stable to heat. ठीक? Lithium carbonate को हम छोड़ दें, which is decomposing on heating, forming Li2. We have already discussed about this heating effect in our salt analysis discussion. ठीक? So moving further, NaCO3 is used as baking soda. ठीक? Now baking soda is just Na2CO3. Yeah. But baking powder is having some other components to neutralize the alkaline pH created by sodium part. Okay, so we have baking powder and baking soda, difference mentioned here. Okay, solubility, both carbonate and bicarbonates of first group are soluble in water. Let me. Our first group are water soluble. Solubility of most of the salts of group 1 decrease down the cheek. As we go down the group, again the story, whenever there is a decrease in the solubility, you place entire credit to hydration energy. Whenever there is decrease, hydration energy. Whenever there is increase, then use the term lattice energy. So here there is a decrease. So you will say that lattice energy has negligible change, whereas hydration energy decreases considerably. And so the solubility decreases. That is the standard format of explanation. If you will keep in mind, you don't have to remember reason for each and every. Okay? Exception.
Assalam.
Yeah. Hello. Okay, I consider that it was an error by someone. So let's move. So exception is the group 1 fluoride and carbonate. Their water solubility increases rapidly down the group. When it is increases, okay, then the reason their lattice energy changes more than the hydration energy. As I told you, that you have to play only in these two, lattice energy, hydration energy. When there is decrease, then you say lattice energy remains almost same and hydration energy decrease dominates. When there is increase in solubility, then what you will say that the lattice energy changes more and the hydration energy, then the hydration energy which is decreasing down the group. Okay, that is standard format you should use. Okay, we'll start from Na2CO3 tomorrow. Okay, everyone. From here, we will do it tomorrow. You
Excuse
all
me,
can.
ma'am.
हाँ दिविजा.
Ma'am, when we were studying that कि KOH is used for CO2 absorption in spaceships and all, so उसमें ये था कि NaHCO3 is water insoluble या फिर it is a solid mass.
Yes.
But here we mentioned that all are water soluble for the S block, for the group 1 and group 2.
All are water soluble, but the solubility of NHCO3 is less than that of KHCO3. KHCO3 is much more soluble. सेम पॉइंट अगर हम अभी क्लास कंटिन्यू करते तो मैं फिर से रिपीट करती कि जो सॉल्वेज प्रोसेस है ना,
Yes,
which is a
ma'am.
method of preparation of washing soda Na2CO3.10H2O. This also is based on the fact that NaHCO3 can be obtained as precipitated on NaCl addition. This is also on the same fact. The solubility of these bicarbonates, if I talk, NHCO3 is less soluble than KHCO3, though both are soluble, okay, but can be
Yes,
precipitated
ma'am.
easily. Now, what happens that if I want to make same method, say KHCO3 na, by solvase, I cannot make because K2CO3, then I cannot make because KHCO3 is soluble, it cannot be precipitated. Clear, Divija?
Yes, ma'am. Yes, ma'am.
Comment. Though both are water soluble. Okay. Anyone else?
Yes, ma'am.
Nothing. So if anyone has doubt, can stay back. Others, you can close for the day. We'll meet again tomorrow and close this chapter. हाँ बेटे, मीनल जोर से बोल.
मैम जो हमने अभी देखा था कार्बोनेट की जो सॉल्युबिलिटी है वो नीचे जाते हुए बढ़ रही है या अब घट रही है?
इन जनरल हम जब कार्बोनेट्स में बात करते हैं और बाइकार्बोनेट्स में, तो ये देखो,
ये ग्रुप 1 के लिए ही है ना?
सिर्फ ग्रुप 1 के लिए. आज अपन सिर्फ ग्रुप 1 का बात कर रहे हैं.
इससे पिछले वाले पीडीएफ में हमने उल्टा नहीं लिखा, मतलब पिछले वाले पेज पे.
कहाँ पर? किधर किधर मुझे दिख नहीं रहा, बता. ये देख, कोई बात नहीं, बहुत सारी इंफॉर्मेशन एक साथ है. नो नीड टू बी सॉरी, जस्ट लेट मी नो इफ देयर इज एनीथिंग. बट दिस इज व्हाट final conclusion you have to keep in mind. Fluoride, sulfate, nitrate, phosphate, bromide, and iodide. For them, from cesium to lithium, solubility is increasing.
Yes,
Okay.
ma'am. Yes,
For
ma'am.
fluoride, carbonate, and bicarbonate, ठीक, down the group, their solubility is increasing. This is again mentioning only for first group.
Okay, ma'am.
Right? सेकंड ग्रुप
Yes,
में
ma'am.
नहीं है, सेकंड ग्रुप में तो फ्लोराइड, हाइड्रोक्साइड एंड ऑक्सलेट है, जिनकी सॉलिबिलिटी डाउन द ग्रुप बढ़ती है और बाकी सब की डाउन द ग्रुप डिक्रीज होती है।
Yes,
पता है,
ma'am.
मैंने करा था मैंने बेरियम, स्ट्रोंशियम, कैल्शियम में, वहां पर
Yes.
अपने, ठीक है।